Hi, I'm Jordan.
And I'm Chris, and we're the Motion Men.
Today we'll be discussing the physics of basketball shoes through friction and traction, cushioning and impact absorption, elasticity and energy return, ankle support and stability, and mass distribution and control.
First, we'll talk about friction. Friction is a key component on the basketball court. It's the force resisting the relative motion of surfaces in contact. Mathematically, it's expressed as the equation shown below, with F sub k being the force of kinetic friction, mu sub k being the coefficient of friction, and N being the normal force. In simpler terms, this equation reveals that the force resisting motion is proportional to the coefficient of friction and the normal force exerted perpendicular to the court surface. Within the context of basketball shoes, designers strategically put together an outsole with material and a tread pattern to augment this frictional force, ensuring that players had the ability to grip and maneuver with precision and prevent slips on the court. In the context of understanding how cushioning works in basketball shoes, we'll dive into the physics of a player's jump. When a player jumps, the material in the midsole of their shoe undergoes compression, meaning it gets squished. This compression phenomenon is described by Hooke's law, as shown below, with F representing the force applied, K as the spring constant, which measures the stiffness of material, X as the displacement from the equilibrium position. So as a player jumps, the midsole material compresses, and Hooke's law tells us that the force involved is directly proportional to how much material is compressed. This compression serves a crucial purpose, as it absorbs the impact energy generated during the jump, acting as a shock absorber that reduces stress on the player's joints upon landing. Following this compression, the material then rebounds, meaning it bounces back to its original shape, and during this rebound, the material releases the stored energy, which is especially beneficial during the takeoff for the next jump. Essentially, this law helps us grasp the relationship between the force applied to the midsole, the stiffness of the material, and how much it compresses during a player's jump and subsequent landing, showing the physics behind effective cushioning in basketball footwear. In order to understand energy return, elasticity is crucial. Imagine elasticity as the capacity of a material to undergo deformation, meaning it can change shape and then recover its original form. This fundamental property is essential for maximizing energy return in various applications, including sports footwear. The formula below shows this, with P elastic representing the potential energy stored in a material when it undergoes deformation, whether it be stretching or compressing. 0.5, which is the constant factor, and it's included to account for the fact that potential energy is stored in a spring or elastic material in this case. It's proportional to the square of its displacement. The factor of 0.5 simplifies the expression and is a result of integrating the force displacement relationship. K is the spring constant, which is a measure of how stiff the material is. A higher spring constant indicates a stiffer material, and a lower spring constant indicates a more flexible material. X represents the displacement of the material from its equilibrium or original position. In the context of elasticity, it is the amount the material is stretched or compressed. So to break it down, when a material deforms, it stores potential energy. The formula quantifies this stored energy, revealing that it is proportional to the square of the displacement. In simpler terms, the more a material is stretched or compressed, the more energy it stores. This stored energy becomes valuable, especially in sports like basketball. Materials with high elasticity are advantageous as they efficiently regain their original shape and release the stored energy. To understand ankle support in basketball shoes, we dive into torque and rotational motion. The equation for torque is shown below, with R as the lever arm, F signifies the applied force. The lever arm is the distance from the ankle joint to the point where the force is applied. The shoe's design, particularly around the ankle, exerts influence on these forces, playing a critical role in furnishing stability. The stability is paramount in averting undue ankle movement and potential injuries. A good designed shoe ensures adequate ankle support, allowing for proper distribution of force and fostering stability amid rotational movement. Consequently, the risk of injuries stemming from excessive ankle rotation are mitigated. Overall, the relationship between torque and rotational motion in ankle support in basketball shoes unfolds as a physics-guided design by manipulating the lever arm and force around the ankle. Now let's discuss mass distribution. The center of mass is crucial for balance. Think of it as the point where the shoe's weight is evenly balanced. We can also use the torque equation here. When the shoe's mass is spread out well around the center of the mass, it helps the player controls their movement better on the court. In simpler terms, having the shoe's weight balanced around the center can make it easier for players to stay in control. How the mass is distributed in a shoe matters for a player's performance. When the weight is evenly spread, it enhances a player's balance and maneuverability, contributing to better control during basketball activities. As you can see, physics is all around us, even in things as simple as basketball shoes. I hope this video helped you understand the relationship between physics principles and how they can elevate an athlete's performance. And just for good measure, here are some clips of what would happen if you were to make these movements in non-basketball shoes.